What I want to do is look at this problem right here in Lagrange multipliers. It says I have a function here that is constrained by this function here. Okay? What Lagrange proved was that whenever you have one function constrained by another and you're trying to find the max or min of this function constrained by this one, he showed that the gradient of this function, which is right here, here's the function, here's its gradient. The gradient of that function is equal to the gradient of the original one it's off by a constant, and we'll call it lambda. Lambda is the Greek letter for L. He didn't name it that. It came later as an honor to him for coming up with this. So essentially, whenever you set the gradient of the, let's call it the master function, is equal to the gradient of the constraint function, whenever you set those equal, they're off by a constant wherever there is a max or a min of f constrained by g. So let me show you this. I'll go through the math here in a second. I want to show it to you graphically. So what we have here is we have in orange, we have the function f. That's in orange here. That's the surface f. F equals x e to the y. And in green here, we have the function x squared plus y squared equals 2. All right? And if you notice, the orange function, whenever we constrain it, whenever we just look at the intersection of it with the green one, with the cylinder, it has a maximum associated to that intersection, and it has a minimum associated to the intersection. Where those are has everything to do with what their gradients are. So what I've done here on the left here is I have a function f and I have a function g. So function f, and then I have all the components to make its gradient. And then here is the gradient itself in orange. Let me see. That's okay. So I have a vector associated to the orange object, what we'll call the master function maybe. This is the gradient vector which points in the direction of steepest ascent. Okay. The left-hand side of the constraint, so here's my constraint, x squared plus y squared equals 2. The left-hand side, I'm going to call that g of xy. Okay, that's actually this. Whenever it's equal to 2, it looks like this. Okay, that versus this. So the left-hand side, x squared plus y squared, that is another function. Its gradient, I've done all the work over here to find its gradient. Its gradient is this vector here. Okay, now I want you to look at whenever I change my points, whenever I'm going around. So A and B here are A comma B is point in the xy plane, and then G of AB, and then F of AB. Where's F of AB? That gives you the actual point itself. So I got a point here, and I got a point here. So those are 2 points in the xy plane. Let me show you. So if I move A and B, you'll see it goes around like this. Okay. Now, if you look, whenever those two vectors point in the same direction and they're off by a constant, whenever the gradient vectors are off by a constant, they will be exactly where I need them to be to find the max and min. So it turns out that one max is at 1, A is 1, and B is 1. I'm going to move those over. And if you look, they're pointing in the same direction, or if they're the negative versions of each other, like one vector is equal to the negative constant times the other. Notice that they're pointing in the same direction, and if I bring that constraint back in, the x squared plus y squared equals 2, look where they end up, and look that they're actually pointing in the same direction, off by a constant, at the exact point, at the F point where there's a max. Okay, now what I'm going to do is move it around again, and it turns out the min, let's go where the min is, it turns out the min is where the other vector points. I think it's this way. I think it's -1, 1. We'll look at the math in a second. Let's get to 1. -1, 1. All right. You see, this red dot is the minimum of the f function. And if you look, let me take off the actual functions themselves. If you look, they're pointing in the exact opposite direction. One is going to be a negative constant times the other. Okay? So what I've done is I've put this in 2 dimensions. What we have here is we have the contour lines, the level curves of the orange function. Let me get that over here. I'll show you what I did here. So let's see, where is it? There. Okay, so the orange function has this contour line that goes through it. See how there's a contour line for it. See, there's contour lines going up and down it. These are the cuttings with the z-axis. All right. Where those contour lines are tangent to the contour line of this green function, you have a max or min. So what I've done here is, this is the green function, this is the view from the z-axis. This is the green function here, and then I have contour lines that are of the orange function, okay? I want you to notice if I take some of them off, if I take them all off, I want you to notice that where it is tangent to the green constraint, we have our, in dotted lines here, these are those gradient vectors. So gradient vector of the green function, and then gradient vector of the orange function. Okay, notice that they are a constant. The green one is a constant multiple of the orange one. It's like smaller, right? And where the contour line of the master function f of xy is tangent to the contour line of the constraint function, you have this relationship between the two gradients. So I'm going to move the contour line to the other side where we found a min. This is 1, 1, and this is -1, 1. If you look at the original here, it was that A was -1, B was 1, and that's where the minimum was. That's where the minimum was. If you look, it was at -1, 1. Okay, now if I move the contour line over, if I keep going, notice that where the see, this contour line is not tangent to the contour line of the constraint, but where it begins to be tangent, that's where the minimum is. And so notice that the vector associated to the constraint is equal to a negative constant of the vector associated to the master function f of xy. In Desmos 2D, it's hard to draw vectors. So I just did the vectors using dotted lines here. Okay, and so if you want to look at the math, what I basically did was I have my gradient of G, I'm my gradient of F, I set them equal to each other up to a lambda, okay? So one vector is equal to a constant multiple of the other. And when I do the math, I end up with, it takes a little while, but I end up with these two numbers here. And so where these 2 points, and so now I'm going to plug those into F. I get E for both of them, which is about 2.7 and negative 2.7. So the max of F will be at 1, 1, 2.7, and the min will be at negative 1, 1, negative 2.7. And then to get those dotted line vectors, I just plugged in the max and min into the gradient vectors, and then I created them from there on Desmos. Now I want you to notice that this 2.7 and this negative 2.7, that is the z value that F attains whenever there's a max. So if we look at this, let's see. So this better be at 2.7, that max. So let's see. Let's pull it over. All right, so that point there, that red dot is at 1, 1, 2.7. Let's see. Where's the red dot? Yep, here's the red dot. 1, 1, 2.718. That's the value of E when you do the math. Now let's go to the other side where there was a min at negative 1, 1, negative 1, 1, and then this better be at 2.7. Let's see. Where's the red dot now? Negative 1, 1, negative 2.7, sure enough. And so that contour line, whenever, see this contour line here, whenever I make that C value negative 2.7, and when I make it 2.7, C value is 2.7, I'm at the max and the min, and that is borne out in this two-dimensional diagram here, where M is negative 2.7, about 2.7. It's hard to, it's kind of not cooperating a little bit. It's kind of hard to see it, but if you zoomed in a lot, you'll see it. It's hard to do because I can't do 2.718. All right, but regardless, that's at 2.7, and then when I make it 2.7, that contour line is tangent to the contour line of the constraint. The constraint has contour lines that are just circles, okay? And then if you wanted to, you could look at the contour lines of G itself, but that basically does it. So in essence, what's happening here is what Lagrange stated was that when you have a function that is subject to a constraint, okay, the gradients are off by a constant at the max or the min. And we just proved that. So I hope that clarifies it some.